This video we will discuss rational functions. Rational functions basically are fractional functions, and one of our rational functions is one of our parent functions, which is just the graph or the function 1 over x. The graph of this is two pieces that look like this, and this point are 1, 1, and -1, -1, and this point in here is kind of like the center point. If we use our graph shifting and we add to the x, what we know here is that this is going to shift it left 5 units. So 1, 2, 3, 4, 5, that asymptote is going to shift 5 units to the left, and we're still going to have that shape that looks like this. For the next example, we know that we're subtracting from the function. So if we were subtracting from the function, we're going to go down 3 units. So our horizontal asymptote moves, and we're still going to have that same general shape, up 1 over 1, back 1, down 1. So we can, if we have that parent function, use our graph shifting to graph these. However, a lot of times we can't see that because of the way that the polynomial is written. So let's take a look at what we would do to graph a rational function. So again, our rational function is just going to be a ratio of two polynomials. To find the domain, we have to set the function, or not the function, the denominator, equal to 0. These are going to be the values that are excluded, and they're also going to be our vertical asymptotes down here. If when we factor the numerator and the denominator, there are like factors that can be canceled, these are going to turn out to be wholes. And from that point on, we work with simplified fraction. That's very important. Horizontal asymptotes can be found by comparing the degree of the numerator and the denominator. So we know that if it's bottom heavy, in other words, the denominator is greater than the numerator, then we have a horizontal asymptote at y equals 0. If the degree of the denominator is less than the numerator, there are no horizontal asymptotes. And if the degree of the numerator is equal to the degree of the denominator, then we just take the ratio of the lead coefficients. And you'll see examples of each of those shortly. Sometimes we don't have a horizontal asymptote, in which case we might have an oblique asymptote, and that is when the denominator is a degree 1 more than the numerator. In order to find that oblique asymptote, we would have to perform the division and then just neglect the remainder. And again, we will see if that happens in some of these examples. The last thing we want to know is whether or not a graph crosses the horizontal or the oblique asymptote. So we know that when we have a graph with a vertical asymptote, that vertical asymptote comes from where the function is undefined. It comes from the domain. And so we are never ever going to be able to cross a vertical asymptote. On the other hand, if I have a horizontal asymptote, I could actually cross a horizontal asymptote, and it might look something like this. It might go above the asymptote and then flatten out afterwards, like that. And then I would have maybe another piece. And similarly, if you have an oblique asymptote, so let's say we have an oblique asymptote like this, we might have a function that crosses and looks something like this. So it actually may cross that oblique asymptote. Additionally, like all graphs, we also want to know what the x-intercepts and the y-intercepts are To find the x-intercepts, we set y equal to 0. And to find the y-intercepts, we set x equal to 0. We may need some extra points, and we'll just plot points as needed. So let's take a look at this example where we want to graph the function, and we're going to work through the steps that I had on the previous page. So we're starting with r of x equals x squared minus 4 over x squared minus 7x plus 10. And I'm going to start by factoring everything. So I'm going to have x minus 2, x plus 2 on the top. And on the bottom, x minus 5 and x minus 2. So for our domain, we know that x cannot be 5 and x cannot be 2. And I also notice that the x minus 2's cancel, leaving me with x plus 2 over x minus 5. Because the x minus 2 canceled, x not equal to 2 is actually a whole. The remaining factor, x minus 5, is going to be our vertical asymptote. So we don't want to say what are the vertical asymptotes? 5. We want to say x equals 5. And we also know that there's a whole at x equals 2, but it would be nice to know what the y value was. So we plug the 2 into this new reduced function. So that will give me 4 over negative 3. Are there any horizontal asymptotes? Well, we compare the degree of the numerator, which is 1, with the degree of the denominator, which is 1, in which case we take the ratio of the lead coefficients, which also happen to be 1 over 1. So we get y equals 1. And if we have a horizontal asymptote, we do not have an oblique asymptote. So we only have the 1. Does the graph cross either the horizontal or the oblique asymptote? So what we do is we set our function, x plus 2 over x minus 5, equal to our horizontal asymptote, which was 1. And I'm just going to cross multiply. So I get x plus 2 equals x minus 5. Subtracting, I get a non-true statement. So in this case, no, it does not cross. If it did cross, then we would get something like x equals. We want to know what the x-intercepts are. So we're going to set y equal to 0. And in this case, the function equal to 0. So x plus 2 over x minus 5. Cross multiplying, we get x plus 2 equals 0, or x equals negative 2. For the y-intercepts, we're going to set x equal to 0, and we will get r of 0 is negative 2/5. Okay. So now we want to put all of this on the graph. So we're going to start here by writing down our asymptotes and our wholes. So we know that we have an asymptote at x equals 5. That's a vertical asymptote at x equals 5. And a whole at 2, negative 4/3. So kind of here. We know we have a y, or a horizontal asymptote at y equals 1. We know that this graph crosses at x equals negative 2 right here, and negative 2/5 here. So I'm going to draw this graph. I can tell right here it's going to go like this with a hole. And it might not be obvious to you what's happening to the right side of that vertical asymptote, but you do have clues there. I know that it's going to be above the asymptote because it doesn't cross the x-axis, and so if it were below, it would have to have another x-intercept, and we don't have that. So it might be nice to know, if I plugged in 6, what would r of 6 be? Well, r of 6 would be 6 plus 2, which is 8, and 6 minus 5, which is 1. So we would be here. Oops, I think I just messed that up a little bit. 6, 8. And we would have something that looked something like this. So we're going to do that again on another example. In this case, we want to sketch the graph of f of x equals x squared plus 12x plus 35 divided by 2x squared minus 50. So again, the first thing I'm going to do is factor. So what multiplies to 35? 1 and 35, 5 and 7. Well, that's lucky. So this is going to factor as x plus 5 and x plus 7. On the bottom, I'm going to factor a 2 out, like that. So it'll be 2 and then x plus 5 and x minus 5. So again, I notice that I have a hole at x equals negative 5, because I would say x plus 5 equaling 0, negative 5. From this point, we're going to work with x plus 7 over 2 times x minus 5. If x equaling negative 5 is my hole, the ordered pair would be negative 5, and then I would plug the negative 5 in to this new reduced. So negative 5 plus 7 would give me 2, and 2 times negative 10 would give me negative 20, so we'll say negative 1/10. Negative 0.1. Vertical asymptotes are going to come from where the denominator is equal to 0. So that is going to be at x equals 5. Don't forget, you need it as an equation, not just a number. And then we'll look at horizontal asymptotes. So horizontal asymptotes, in this case, the degree of the numerator is 1. The degree of the denominator is also 1. So we take the ratio of the lead coefficients, which is 1 over 2. We want to know if it's going to cross that horizontal asymptote. So we're going to set the function equal to the horizontal asymptote, and we're going to cross multiply. So 2x plus 14 equals 2x minus 10. And again, we get something that is not true. So the answer is no, it does not cross. For our x-intercept, we'll set the function equal to 0. And we'll get x equals negative 7. For the y-intercepts, we'll let x equal 0, and we'll get 7 over negative 10. At this point, we will put this all together on a graph. We're going to start with our vertical asymptote at x equals 5. So I'm going to put that here in blue. We have a vertical asymptote here at 5. We have a horizontal asymptote here at 1/2. We had a hole at negative 5, negative 0.1. Our graph is kind of small, so we'll just put a circle there. We have an x-intercept of negative 7 and a y-intercept of negative 7/10. So we have one piece of our graph looking like this. And we might not know what it looks like on the other side. Again, there are some clues. We know that it's going to have to be above the horizontal asymptote, because if it were below, we'd have to have another x-intercept. And if we wanted to, we could find just one more ordered pair. So if I find the function value at 6, and I plug 6 in, I'll get 6 plus 7 over 12 minus 10, which is going to be 13 over 2, or 6.5. So at x equals 6, I would be at 6.5, and I would get another piece that looks something like this. Let's do one more example.